Okay, everybody, I guess we can start now. So, good evening, good afternoon, good morning. Uh, on behalf of Plaksha University, I'm delighted to welcome you all to our Tech Talk today. My name is Ashish Gupta. I'm one of the founders and CEO of Benori Knowledge, as well as a founder and trustee at Plaksha University. Plaksha University is an initiative of 80 plus tech leaders and entrepreneurs to set up a university to reimagine technology education. One of our big goals is to use cutting edge technologies to solve some of the biggest challenges which our society faces. Plaksha, the campus will be coming up in Chandigarh, and we are most likely going to open up next year in the year 2021. In our inaugural year, we will offer exciting majors such as computer science and artificial intelligence, robotics and cyber physical systems, biological systems engineering, as well as data science, business, and economics. With Plaksha Tech Talks, our mission is to get eminent speakers and experts from all over the world. These are people who are really at the forefront of using technology to solve challenges that we face as a society. For our talk today, we are delighted to have Dr. Bhaskar Krishnamachari with us. Dr. Krishnamachari is a professor of electrical and computer engineering at the Viterbi School of Engineering, University of Southern California. He received his BE from the Cooper Union for the Advancement of Science and Art, and his MS and PhD from Cornell University, all in electrical engineering. He serves as the founding director of the USC Viterbi Center for Cyber Physical Systems and the Internet of Things, and as co-director of the USC Center for Human Applied Reasoning and the Internet of Things. He works on the design of algorithms, protocols, and applications for the Internet of Things and distributed systems. He has co-authored more than 300 papers and 2 textbooks, which have collectively cited more than 25,000 times. He has been cited more than 25,000 times. He has been a co-recipient of several Best Paper Awards. He has received the NSF Career Award and the ASEE Terman Award for Outstanding ECE Faculty. In the year 2011, he was featured in the MIT Technology Review's list of top 35 innovators under the age of 35 and in Popular Science magazine's Brilliant 10 in 2015. During the talk, Dr. Krishnamachari will be speaking for about 25 to 30 minutes. This will be followed by an interactive Q&A session. Feel free to put up your questions as and when they come to your mind. Please use the Q&A feature on Zoom to put your questions, and please not on the chat feature. We would appreciate it if you could also put up your name and designation along with the question. It is indeed my pleasure and my honor to welcome Dr. Krishnamachari. Bhaskar, thank you for doing this. Now it is over to you.
Thank you so much, Ashish. I really appreciate the opportunity to speak to you all. So I'm going to talk about engineering the Internet of Things. This is an area that I've been studying and researching and teaching for nearly 2 decades now at the University of Southern California. So it's really a pleasure to talk to you about what's been really at the heart of my professional career for so long. So before I start, I do want to give just a very brief introduction to my university. I don't know how many of you are already familiar with it. USC is the oldest private university in California. It's older than Stanford and Caltech, for example. We have more than 45,000 students, of whom a very large number are international students, and in fact, many of whom are from India. The USC Viterbi School of Engineering, where I teach, is a very strong school of engineering with many disciplines, including electrical and computer engineering, computer science, as well as world-class programs in even astronautics and others. In addition to our School of Engineering, we have a about 22 other schools, including arts and sciences, and business, law, etc. So it's really quite a diverse school in that regard. I have been involved with a center at USC that is called the Center for Cyber Physical Systems and the Internet of Things. And hopefully by the end of today's talk, you'll have a good appreciation for what cyber physical systems are and what the Internet of Things is all about, and also its connection to other topics like robotics and connected vehicles. So the title talks about engineering the Internet of Things. So the operative word there, of course, is internet. And I wanted to start with a little bit of history. So the internet that we all take for granted today on our cell phones, being able to browse the web, participate in social media, and attend this talk, and for me to be able to communicate with you, really had its beginnings in the 70s, late 60s and early 70s, in what was then called the ARPA network. And this ARPA network essentially was a collection of research institutions and universities having computers that were networked together across the US initially. And I've circled here on an early map of ARPANET. This is from May 1973. Two of the computers on what was then kind of the beginnings of the internet, which were both located at USC. So USC has had a very long connection with the internet as it stands today. And this is kind of a bit of a historical note that there was a time when we could, draw the entire internet on a map and literally point at every computer that was connected to it. Today, this is a visualization that captures just a small piece of the internet. It's grown to something dramatically more complex, perhaps more reminiscent of the neural networks in our own brains. Hundreds of millions of computers networked around the world with all kinds of capabilities in terms of the network speeds, the types of routers that we have in place, and so on. And yet, if we look at the what we call the internet, what has made it last all these decades? If you go back to the 70s to now, 2020, we're talking about nearly 50 years of this network growing and thriving with all kinds of applications that we're all used to. And something that I always teach my students about the internet, if you only remember one thing about the internet, you should remember this picture. And what this picture shows is the way in which this network was designed from the ground up to last. So what we have in each of these sort of boxes in this hourglass are different technologies and protocols. So the very bottom, at the bottom half of this hourglass, we have network technologies. And these are what are called the link layer and the physical layer of the internet. They consist of, these days, radio technologies like our cell towers and Wi-Fi. But, when it began, there were different communication media like twisted pair and coax and more recently fiber optic cables, etc. They're all part of what these networks run on top of. But the way the internet's been designed, it's not specific to a particular link or physical layer technology. So we can keep evolving the bottom of this hourglass, and we have done that. So back in the 70s, when the internet was first conceived, we didn't have LTE and Wi-Fi, but changing things at the bottom doesn't change the internet. Likewise, if you look at the very top of this hourglass, we've got applications. And the applications we use the internet for today, from e-commerce to social media to entertainment, or just web browsing and web search, didn't exist in the 70s either. And again, the way the internet was designed with this hourglass architecture, you could have changes at the top in terms of what applications ran on it, and it would still be the same internet. What connects the top part of the hourglass with the applications and the bottom part of the hourglass with the different types of networks is IP, which is the internet protocol. So long as we have a stable waist, if you will, of this hourglass architecture, and we follow the principle that everything runs on IP, by which we mean that all kinds of applications that are coming up are able to use these protocols that are built on top of the internet protocol. And so long as IP can be made to run on every new type of network that shows up, we will always have the internet. And so, so this is really what we're starting with is, the internet as it was conceived in the 70s and still going on. But if you really look at it, perhaps the peak of the internet as we know it today really happened technologically around 10 years ago, when a good portion of our planet became connected to the internet through our mobile devices. And we've primarily used the internet, we continue to use it primarily for people-to-people communication, whether it is in real time like we're doing right now, or via asynchronous social media or web posts. Primarily the content that is on the internet is being created by humans and consumed by humans. But what we've started to see is a shift from this internet primarily focused on people-to-people communication to an internet that also includes what we're going to be calling things, and I'll expand on this in a bit, but essentially increasing connectivity of machines and sensors and actuators to the internet. And now the content that is on the internet will increasingly be produced by machines and potentially even consumed by machines on the other end of it. And the population of the world in terms of the people in it is a little over 7 billion now, but the number of things that we will connect to the internet has the potential to be more than 2 orders of magnitude higher than that, if not even higher, going forward. So what is this Internet of Things we're talking about? We're talking about connecting sensors and actuators and electronic appliances. As I'll point out, what this is allowing us to do is interface the cyber and digital world with the physical world. A sensor fundamentally allows us to measure something in the environment and convert it to a digital format. An actuator, in the other direction, takes digital information and converts it into some change that we can make on the physical world. So if we can have more sensors that are connected together over these large networks, the benefit is that we have a far greater awareness and visibility into the physical environment, as well as, in fact, some of these sensors could even be on humans. So we may even have much better visibility into our physiological, emotional, and cognitive state. And the number of applications one can design which leverage this type of cyber physical information are in many ways a lot higher than traditional applications over the internet. So the cyber physical interface, as we refer to it, essentially is connecting our planet to the world of digital technologies, from computers that can be used to process the data, to the communication network, storage of that data, visualization, and the decision-making that we're doing on the cyber world. Connecting it to the physical world requires essentially a two-way exchange, where we need sensors to be able to sense, measure, and track what's happening in the world. And we need actuators to be able to actually make changes in terms of motion or other forms of actuation. So sensor technologies have played a big role in this ongoing revolution towards creating an Internet of Things. We have all kinds of sensors that can measure some physical phenomena and convert it to digital format. But the other aspects of the cyber side of the cyber physical systems have to do with connecting these things, these sensors and actuators, through wireless networks of various types, through what we call edge computing capabilities, and then connecting it through the network that we have already in place, the internet, and new protocols that have been developed for it, to cloud services where we can gather large amounts of data and process it and analyze it and make sense of it, and then take action as needed based on the application. So when we talk about the Internet of Things, these are some of the applications that it encompasses. And really, these applications are just a small sampler of what is possible with this technology. We have smart homes that many of us are hearing about and starting to see, where we have electronic appliances, within a residence that are being networked together, that are sensing, that are becoming smarter as they are endowed with more intelligence to for example, cool the environment in advance of our even being there to just the right temperature, getting the lights configured, etc. You may not think of it, but apps like Uber and Ola are also IoT applications because fundamentally they draw on the sensor technology of the GPS in our phones in order to be able to identify the locations of where the riders are, where the drivers are, and to be able to match them and do the the pathfinding and the market matching, etc. And so at its core, it's really a sensor-driven network technology. We are seeing something called the industrial IoT showing up in our factories, where we're using sensors to detect, for example, the condition of machines in terms of their wear and tear and replacement of parts and preventive maintenance and so on, where if you could embed sensors at a fine granularity and detect where the problems are and treat them before your parts break down, you can really keep your assembly floors kind of running in the most efficient manner. We see the Internet of Things also showing up in our urban environments. For example, there's been an IoT deployment in the city of Chicago called the Array of Things, where they've deployed a number of environment sensors, including air quality sensors and others, to be able to give us very fine-grained understanding of what's happening in terms of air quality and to be able to act on that. We're also seeing the emergence of car-to-car communications and car-to-infrastructure communications and the capabilities that could be provided if we are also taking the measurements and the sensing that's happening on the road by the cars and leveraging that. For example, when a car goes over a pothole, the acceleration and the vibration of the car can tell us about the location and the severity of that pothole, and you could communicate that in real time and be able to form a very accurate picture of the condition of your roads 24/7. We're seeing IoT also deployed in the context of agriculture, where sensors can tell us when to water, how much to water, what nutrients are missing in the soil, so that farmers can really increase the yield of their crops and be able to ensure the most productive output from their farms. So these are, kind of a small set of applications to show you the breadth of what IoT is about. I think of it always as a very interdisciplinary subject. Even within engineering, it calls upon many fields such as wireless networking, from hardware design and computer engineering to robotics and cyber-physical systems. Blockchain technologies have a role to play here, as does, of course, a lot of research and technology that has to do with privacy and security. So in what follows, what I'm going to do is just tell you or show you a few examples of research into IoT that we've been doing at USC. My lab maintains and operates one of the oldest and the longest running IoT network testbeds in the world. This is a testbed that consists of very small, sort of these wireless embedded devices, which have microprocessors and sensors and low power radios on them, deployed in a building on campus called Tudor Hall, hence the name. And here's kind of a visualization of this testbed. And you can see on the left and right, two sort of instantiations of this network running on different channels. In the figure on the left, we're seeing this network and all the links are basically wireless links between pairs of wireless sensors being affected by the ambient Wi-Fi usage in that building. So it's an indoor deployment, and we're studying essentially how the channels are affected by interference from other wireless networks. While the channel condition on the right, where it's all green, these links are doing well. They're not as affected by the ambient Wi-Fi network. So this is a test bed that we use for a lot of implementation and evaluation of software protocols for routing data through collections of sensors. The idea is that your individual devices are not so capable, but if you can deploy large numbers of them in a building, you may be able to do interesting things with it. One thing that you can do with sensors like that in a building is you can create a way to detect the location of people at a fine granularity within a building. Now, many of us are, if not all of us, are familiar with the use of GPS. If you're outdoors, you're going somewhere, you can turn on your GPS and it'll help you locate yourself and help you get where you're going. But it turns out GPS, which is a satellite-based technology, actually doesn't work well indoors. If you're inside a mall, if you're inside your homes, you turn on your GPS, it actually won't give you very good resolution location because the satellite signals actually can't penetrate through ceilings and even foliage. So the algorithms that we've been developing actually use geometry having to do with the location of wireless devices, and here represented by these blue dots, as well as patterns created by their radio transmissions. Essentially, the algorithms that we've developed tessellate the space into different geometric regions, each of which has a unique wireless signature. And we use this wireless signature to locate ourselves in that environment. So this is a class of indoor location algorithms that we've developed at USC called sequence-based localization. And here's on the right some examples of real data that we've collected from running our algorithms. You can see the figure on top showing an individual student kind of walking through the hallways of one of the floors of our building. And with the sensors that we've deployed, the network that I showed you earlier, we're able to initially generate a coarse estimate of that student's movements. And then when we correct for the map and we know, for example, in given a map and walls that the student couldn't be wandering through walls, we're able to kind of fix the path down to the hallway, and the figure at the bottom, essentially on the right, shows the movement of the student through the hallways as it happened. And we're able to get this sort of meter scale accuracy inside a building, which you wouldn't be able to do with GPS alone. We've been developing a number of other pieces of software that allow for these types of fine-grained indoor localization. And it's useful not only for humans to locate themselves, but you can also imagine maybe goods in a warehouse being tracked using similar IoT technology. IoT also intersects very closely with robotics. You can imagine that the things that we're talking about are robots. They may be communicating with each other wirelessly, locating themselves, and measuring something in the environment or changing something in the environment. And our interest in this space has had to do with networks of robots where the robots are talking to each other and coordinating and communicating. Here is a visualization of a test bed that we have at USC to tinker with kind of networks of robots. And so these robots are completely wireless. They don't even have a camera on board. They are simply understanding their relative location with respect to other robots through sensors that are deployed on board, having to do with ultrasound and radios. And we're essentially getting them to talk to each other wirelessly and coordinate their actions. Here's another kind of a short demo of a tracking robot, where the robot in the back essentially has a miniature radar installed on it that we've come up with, that allows it to track the robot in front of it without having any explicit communication in this case. And you could imagine this type of technology being useful for example, in the context of rescuing people in a building that's on fire, where if it is dark or smoky, you won't be able to get line of sight and camera-based tracking by a robot that's carrying equipment for a firefighter. But you can imagine having a robot that's simply able to detect the location of the firefighter through beacons being sent by a radio in their pocket, and is essentially following close to them, like the robot behind here is doing. We'll just imagine at a larger scale, carrying firefighting equipment or rescue equipment for them. And so again, with embedded devices, computing, sensing, and actuation, as well as wireless communication and sensing, we're able to build this type of automated tracking systems. Another project that we've been engaged with at USC in collaboration with the city of Los Angeles is to build what we call a marketplace for IoT data. So if you think about this large volumes of data produced by sensors, whether they are air quality sensors or sensors detecting parking, it may be of interest for people to build an application for the city that can leverage the data coming from these sensors. But how do people find the data that they're interested in? And if the data belongs to someone else, how can they pay for the data that they want to use? So these are questions that we address by creating a marketplace for these types of data streams. So to give you an example of what this would be good for, we have in the city of LA a number of different sources of data for parking availability. We might have meters on the side of the road that tell us whether individual spots are available. We might have parking garages where there are sensors placed that can tell the private garage operator how many spots are currently available. And you might have, for example, at the airport, some public organization that's maintaining the parking structures that is aware of the parking occupancy. So if all of them could contribute their data to a marketplace such as i3, the system that we've developed, then someone that's building an application for finding available parking near a driver would be able to collect the data that they need from different sources, pay for that data, and then make available a service that the end consumer really cares about, which is no matter where I am in LA, I want to know what parking is available near me, and if it applies, like what would it cost to pay for parking and so on. But in order to integrate these data sources coming from very different sources, having a common marketplace platform for data would be really useful. So this is kind of a visualization of this i3 platform that's a community marketplace for IoT data. You have sensor owners and data owners who are plugging into this platform to provide their data in exchange for some incentive. You have application developers that consume data from this platform and they pay the data owners. And you may also have some data brokers that come in and buy raw data from the platform, run it through some machine learning and AI algorithms, and turn back kind of processed and analyzed data back to the platform. And so operating these types of data marketplaces for different communities, different cities, we believe is kind of the wave of the future when it comes to how IoT systems will scale up to entire cities. We have deployed these types of large-scale sensors at the USC campus. Everywhere you go on at least the engineering part of campus, you'll run into some of our nodes, which are measuring everything from air quality and humidity and temperature to even just sort of ambient sound levels. And we use it to evaluate our ideas. Another project that we've been engaged with is looking at sensing of the human body, in particular to do with emotional and physical wellness and cognitive loads, using wearables and other sensors that are emerging. The application we have is towards personalized learning. So if we, through, for example, a wristband, if we're able to measure physiological signals that tell us about the cognitive load on a student, the emotional stress they might be going through, it might help teachers in the classroom better adapt their teaching. It might even help the learners figure out, when is a good time for them to focus more on studying something versus when is maybe a good time for them to step away and take a break. And we think that learning that can really be personalized down to the individual and adaptive to their cognitive and emotional state is likely to be much more effective. And so that's a place where the IoT technology is coming in on the sensing and the processing of the data, and then the application of what we learn from the data back into the educational environment is something that we're exploring. And I should mention, this is actually a collaboration with our School of Education at USC called the Rossier School of Education. And I'm involved with the center that's a collaboration between engineering and education at USC. Just another example has to do with connected vehicles. You can imagine cars equipped with their own personal UAVs that can dash out ahead of them and maybe look around curves or get kind of an aerial view of traffic ahead of them. And could you communicate in real time back to the driver what is on the road ahead? We've built in collaboration with General Motors, systems that take images from a drone from above the car, looking far ahead of it, and in real time be able to process that data and communicate back to the driver, just some simple information like the road is congested ahead of you, or watch out for dangerous road conditions, or watch out for a high-speed vehicle coming towards you, etc. And to be able to do this in real time, you need the sensing, the camera component, you need the computation that needs to happen to process that data in real time, and so on. Let me kind of, to wrap up, just a brief tour of our research, mention also some ongoing work in the context of the COVID-19 epidemic. IoT devices, including our own phones and potentially other sensors, can be used to detect when other devices are nearby through Bluetooth signals. And back in March, I actually proposed protocols that could be used to make sure that we are logging these contacts between individuals that are close to each other, and using that information to notify them if later on it's found that some individuals are infected by COVID, so that they can take some measures to be quarantined or treated. And these ideas that we developed and proposed in early March, in fact, ended up being adopted by Apple and Google. You may have heard of the exposure notification APIs that Apple and Google have developed that came out of, or at least was informed by some of the research that we had done, and also other researchers around the world. Just to wrap up, I want to just briefly introduce to you the center that I run at USC Viterbi. It is an intersection of various technologies related to cyber-physical systems and IoT, and application domains that they're relevant to, from transportation and energy and healthcare to smart buildings and smart cities. We have a number of faculty in engineering and other disciplines that are collaborating to work on IoT and cyber-physical systems and these related topics that I covered today. So with that, I'll stop, and I'm happy to take any questions as well. Thanks.
Hi, good evening, everyone. Thank you so much for that talk, Professor. It was extremely interesting to hear about the far-reaching applications of IoT. My name is Siddhant Oswal, and I'm a member of the Plaksha program team. I'll be moderating the question and answer session along with Ekamjot Kaur from Carmen Common School in Chandigarh. Ekamjot was also a part of the Plaksha summer school program, Young Tech Scholars, and we're really, really excited to have her here. We're now opening questions to the audience. You can send in your questions by using the Q&A feature located in the menu options towards the bottom of the screen. It would be greatly appreciated if you could also include your name and designation towards the end of the question. To start with the questions, we'd asked our audience to send in a couple of questions prior to the webinar. So Professor, the first question we have is from Akanksha, who asks, what inspired you to specialize in this field, considering that it only emerged in the public eye over the last couple of, last 5-6 years?
So, I mean, it's kind of, I could talk for hours in just this one question, but I think the short answer, and really something that particularly the young folks in the audience might want to keep in mind, is to follow your interests, right? So at any given time, what your interests are might be different from what it will be at some later time. But if you're very deeply engaged in whatever it is that interests you in the moment, it always leads you to exciting things. That's been my experience in life. So I think I started out with a general interest in mathematics, going back to my school days in India. And that kind of led me to the sciences and to engineering. I, along the way, also had an interest in programming and software and computers, and so ended up kind of picking computer engineering as a focus. Then at some point I got interested in communications. It was a class that I took as a ECE student. And then I was also interested in this new emerging field of artificial intelligence. And so just constantly following my nose and seeing what is interesting here and what's exciting, and getting to wanting to learn more about it just kept me kind of moving step by step towards the more interesting, more exciting areas of computer science and computer engineering. So I've been working on this topic, like I said, for almost 20 years, way before it emerged in the public eye. But that kind of came through just being curious about and following, what is the most interesting thing at the moment, at each moment. And so you can't predict right now what will be an important topic 20 years from now, but you can certainly ask yourself, what am I excited about right now that I want to keep learning? And if you just keep following that, you'll always be at the forefront, I think.
Thank you, Professor, for answering that question. The next question we have is that in a country like India, how might the infrastructural constraints have an effect on the development as well as the implementation of IoT?
That's a great question. So, we do think hard about what of these technologies are really addressing, the needs for a wide range of populations and environments. The first thing is that I actually think it is precisely places which don't have a lot of existing infrastructure that benefit from IoT technologies, because connectivity and setting up connectivity through wireless communications and networks is relatively cheap in many ways. Deploying sensor technologies is relatively cheap in many ways. Like information technology and digital technologies are often not the most expensive thing to get the ball rolling. And so you can see the benefits from the deployment of technology, and that in turn will drive development. So it's not that you have to have all of the infrastructure in place and then deploy information technology. You can actually use information technology to drive the development. And I think, maybe it's possible that someone who was looking at India 20 years ago wouldn't have foreseen how widely used cellular technologies are today, right? It's everywhere. But the reason it's everywhere is that it's relatively cheap. It's very easy to create these communication links and so on. And I think sensor technologies have a lot of that as well. So you don't need heavy infrastructure in place before you can apply sensor technology to improving our farms and their productivity. You don't need heavy existing infrastructure in order to be able to deploy them in our cities to improve our tracking of the air quality and improve the environment. We don't need heavy existing infrastructure to be able to deploy, I would argue, IoT systems in our factories to make them more productive. And you can just, case by case, looking at a particular sector, look for the opportunities where relatively low cost technology can give significant productivity improvements. And we don't have to wait till everything else is in place before we adopt and find good uses for the technology.
Thank you for answering that question, Professor. Our next question comes in from Ishan Saha, who's a student, and he'd like to ask your views about how the perception of IoT, about automation, is often that alongside AI, ML, IoT, does it pose a threat to jobs? Does it pose a threat to the world? He'd like to know your thoughts about that.
That's a wonderful question, and I really appreciate the student who's asked it. I think the important thing to keep in mind is that technology in many cases is a double-edged sword, right? So there's a lot of potential for the benefit that it can bring to society, but there's often really multiple threats or sources of harm that the technology brings with it as well if it's not used properly. When it comes to IoT technologies with all the capability of pervasive sensing, I would say the number one threat has to do with what's sometimes called creating surveillance societies, that we end up using these sensors to spy on people, to invade their privacy. That's really a big concern and growing in many parts of the world. And so there has to be mindful use of the technology. There have to be regulations about what it can and cannot be used for. So that's sort of one aspect of it. There have to be actually improvements in technology to address that type of harm, whether it has to do with better privacy sensitive data gathering approaches and data computation approaches, or better security for the IoT systems that we deploy. The other concern that technology does bring up has to do with the role automation will play in the jobs. And on the one hand, it promises to improve our productivity, economic productivity. On the other hand, that productivity can come from replacing the work that was previously done by humans. And there is an analogy to be drawn to the industrial age, where the automation that was developed actually did in fact negatively affect a whole industry of artisans and workers that worked with their hands, and what they produced individually was somewhat more inefficient, but in many ways better skilled work that was no longer needed when factories were mass producing cheap, perhaps not such good quality goods. And there was a long period of time where that posed a societal challenge also. And it's not out of the realm of possibility that we'll face similar challenges as we see more robotics and other technologies coming up. I think part of the answer there is that even as it displaces traditional work, it also creates new opportunities and new types of work, right? And we have to be thoughtfully engaged in figuring out what are these new opportunities that we can put people to work, and meaningful work that they care about, that is a source of livelihood, but also a source of almost spiritual satisfaction in doing that work. And so how to find that balance between technologies displacing existing work versus creating new types of meaningful work. I think that is a challenge that we have to actively engage in as we introduce new technologies. And I think that conversation goes beyond pure engineers. It goes beyond pure engineering to the whole of society. So all of us have to be constantly asking these questions and challenging to some extent, the use of the technology and regulating it as needed to make sure that it's helping us as a society.
Thank you, Professor. We have the next question by Abhay Chaudhary. The question is that how can one maintain data privacy while developing Internet of Things?
So let me give you a concrete example. So I mentioned this COVID-19 contact logging application. I'll give you that as actually an example of exactly this question. So it was actually around early March that I got really concerned with the growing number of COVID-19 cases. And I could see already in early March this was going to be a worldwide challenge. The traditional way that we deal with epidemics and try to contain it is to do what's called contact tracing. When someone gets infected, if we can find out quickly who else this person came near, and we can get them to self-quarantine or get access to medication quickly, we can help slow down the spread, if not contain it. The challenge is that traditionally the way contact tracing was done was individual, it was very manual. Basically, you would talk to the person, somebody that's a medical professional would talk to the person and ask, who did you come into contact with, and make phone calls to every one of those people and so on. Or maybe knock on their doors to get in touch with them. So an obvious question to ask is, how can technology help? Can we automate the process of figuring out who you've been in contact with? So it turns out we're all carrying with us a device, this mobile device, that is capable of literally sensing who is near you, because it has on it a Bluetooth radio. And these radios periodically beacon and can be heard by any other mobile device nearby. So if everyone just had their mobile device logging this type of contact data, they can use it to automate. When they get sick, you can automatically collect who else was near you, at least a good number of them, from the Bluetooth logs that might have been collected. The challenge, however, is privacy. So if we require everybody to download such an app that runs contact logging, you're essentially asking everyone to constantly spy on everyone else. And so if you want to do this in a way that preserves privacy, the data that's being beaconed has to be anonymous. And so what I was proposing in March was a technology where you encrypt or randomize the data that is sent over the air. So there is no, in fact, the way the schemes work, nobody ever records exactly who was near them, only that they got a particular identifier that's randomized or anonymous. And later on, when someone is sick, they upload the logs of their randomized data to a server, and everyone's device can check privately with the server if the data that's stored indicates that they might have been in contact with someone that's infected, without even revealing who was the person that was infected. So by thinking carefully about the problem, we can come up with an alternative that is privacy sensitive. And I think this goes to show that if you can put a little bit of thought into like, what is the privacy concern? How can I address it? We can address it to some extent technologically. Now, that may not be the full picture unless there are regulations in place that prevent commercial operators from collecting private data. They will do so if it's to their benefit commercially. And so you also need regulation and laws in place that minimize the harm that can be done by the collection of private data. And then technology can help address what else can you do that's privacy sensitive.
Thank you for answering that question, Professor. I think that it's extremely relevant given the times that we find ourselves in today. The next question is also COVID related. This is from Mr. Abhishek Tomar, who is AGM at HCL Technology. He asks, how do you see IoT playing a significant role in the transformed society post-COVID?
So that's, I think, definitely an open question. All of us are wondering how significant are some of the changes we've experienced in how we work and how we communicate and how we learn this year. How many of these changes will stick post-COVID? These are conjectures, but I'll put them out anyway. I do think that we've become more comfortable in at least some areas of our economy working remotely. It might drive a trend towards greater de-densification. So instead of everybody, gathering together in urban environments, maybe we can de-densify, which will be good for the environment in many ways. A lot of our air pollution and congestion of traffic and many of the things that we've seen over the past several decades are a result of densification. So to the extent that technology can help with de-densification, that'll be great. But again, to refer back to one of the projects that I mentioned, the one about personalized learning might play a role, right? So if we can have IoT technologies that can give us some insight into the cognitive and emotional state of someone on the other side of this video call, then perhaps the teaching, for example, experience online could be a lot more personalized and better customized to the individual learner, which to some extent is possible when you're in person because you can read the room, you can see these 30 people in front of you, you can talk to them, you can, but not just can you talk to them, but you can also almost sense when people are looking, bored or distracted, and you can adapt your presentation accordingly. But it might be helpful, for example, just to throw out an idea, it would be helpful to almost see like in real time, 90% of the students right now are tuning out of whatever you're saying. And if I had that kind of feedback, perhaps it would help me change the way I present as I'm teaching. But I do think that there are changes and having to do with even how we organize our indoor spaces and so on, where I think IoT technologies will play a role.
Thank you, sir. We have the next question by Shivanshu Srivastav, who says that can computational modeling of human cognition be linked to IoT technology?
Absolutely. And in fact, that's one of the last frontiers for science and engineering is actually understanding ourselves, understanding our brains, how they work, how our emotional responses, our cognitive responses are linked not only internally, but also to the environment that we react with. And it's a combination of technologies that tell us about our physiological signals. So in the personalized learning project, for example, we've been looking at sensors that measure your skin temperature, your skin's resistance, which says something about your emotional response to things. There are sensors that measure the level of activity in your brain. And if we can decode these signals and tell us a little bit about, how the cognitive processing and the emotional processing is happening and how that's linked with our environment, we may be able to make our environments more responsive to our cognitive and physiological states. And that kind of link between the human and the environment that we're in, whether it's a car, whether it's a building, whether we're outdoors, can be made a little bit more tighter. It can help us be healthier, learn better, interact better, have environments keep us more comfortable, and so on.
Thank you for answering that question, Professor. On a related note, the next question comes from Mr. Dharmesh Prasad, who asks about the ethics of related to IoT and AI. He asks, for instance, how would connected cars decide who to avoid in case of decision to choose between two objects, which may even be two humans?
So first of all, I think, as we talked about earlier, this link between technology and ethics is it cuts very deep. And I will also say that so much of technology development does happen in a vacuum, meaning there are researchers developing the technology with kind of its promise in mind. There are companies that deploy it with profits but also I think the customer in mind to some extent. But ultimately, each step that we take with technology often is very myopic. You just say, like, right now, what would be the next thing I should do that improves my bottom line or that, you know, helps my customer? But you often don't take like a bigger view of the ethics associated with it. And we often come to learn about these ethical problems after the fact. But I do think that in the last decade, that conversation has started to shift, particularly with the conversation around ethics of AI, bias in machine learning algorithms, and for example, the question that's raised by the audience member about the ethics to do with an autonomous vehicle making decisions that ultimately impact on the lives of other humans. You know, what would be the challenges and how would you go about addressing them? So there's a few things there to unpack. One is that let's keep in mind that the reason we're putting or thinking about putting autonomous vehicles on the road is that in fact our roads currently are not very safe. If you look at least in the US, that I'm aware of the statistics, traffic accidents are actually one of the leading causes of death in the society here. So to the extent that that technology already reduces the overall level of fatalities on the road, that's the big win, right? That's the reason to even pursue it. We shouldn't be going to fully autonomous cars if we're not getting orders of magnitude reduction in deaths compared to today. So you know, the moral dilemma of a particular car being faced with having to hit one individual versus another and having to make that decision is certainly scary, but let's keep in mind that the reason we're building it is that hopefully the overall number of people dying anywhere due to accidents is a lot lower with this technology. But in addressing specific situations like we're talking about, I think the onus is very much on the engineers and the designers to have thought through these ethical issues, to have built-in safeguards to the best of their abilities that are at a level that are acceptable from a society's perspective. That if there are algorithms ultimately that go into such a calculus, that they are transparent, that the public is aware of them and are accepting of the use of such technology. And I think that goes a little bit also to what's scary about technology to people is that we don't even know what it is that's happening behind the scenes. And so how can we make that transparent, I think, is one of the challenges for engineers as well.
Thank you, Professor. Talking more about applications and the interdisciplinary use of IoT, we have a question from Sharad Mathur and Gauri Anupama, who say that what are the modern day prospects in biotechnology? And also, what is your take on balancing the use of technology in the medical field where human interaction is extremely important?
Yeah. So I think this whole area of kind of the intersection of IoT and the medical space is still in its early stages, very much in its infancy. I think applying sensors and actuators in the medical environment, there's so much scope for new work to be done, new kinds of devices to be created, new technologies to improve our processing of the data collected by devices in a medical environment. It's an area that some people have referred to as the Internet of Medical Things. They could be simple, additional sensors that are placed on patients that allow them to be mobile while they're being monitored, allow the monitoring to happen even remotely. So not just when a patient shows up to a hospital and is getting themselves tested, but really they have something on them that allows the monitoring, for example, of their ECG signals 24/7, and if there were anomalous conditions, to be asked to come in, for a doctor's visit. I think we're going to really over the next 2 decades be uncovering new, not just devices, but also new insights about our brain, our bodies through these types of sensors. And that's going to, in my view, change the nature of medical care. I think a lot more of it can be done ahead of time than after the fact, that we don't have to just show up to hospital when we're really in a desperate situation, but the technology brings us to a point where we can be much more proactive about taking care of our bodies. For someone that's really interested in this direction, I think this is a absolutely wonderful time. In fact, going back to the first question that we were hearing, for someone who's broadly interested in medical technology, now's the time to just focus on what your interest is, and kind of stick with it. And I think in the next 10, 20 years, there's so much that's going to happen in that space.
Thank you, Professor. Absolutely. Like you mentioned, healthcare, medicine, and marriage of those sectors to engineering are the future. So given the paucity of time, I'll be combining the final two questions. We had quite a few high school students as well as educators attending the webinar today. So I'm going to be combining a lot of the questions they asked. The first one would be, what career advice would you have for students who want to pursue careers or research in this field? And the second one from educators is that what are the key steps that an educator needs to capture in order to teach students about Industry 4.0, IoT, and related concepts in the modern day classroom?
Great. Wonderful questions. I think absolutely something that we hear from students and educators all the time. I think, the main advice I have is that we live in a time of exponential change. Technologies are accelerating, very rapidly, and the best way that you can be prepared for this time is to be a learner, to be a constant learner, to be someone that's really someone that really thrives on constantly learning new things and adapting what they know, what they do. That you shouldn't approach your education with the mindset that you're going to go to college for 4 years, you learn everything there is to learn for the rest of your life in those 4 years, and you'll get to a job and you'll have that job for life. I think, because of this fact that we're living in such a time of accelerating change, you're going to have to keep learning and reinventing yourself as the careers and the world around you keeps changing every few years. And so think of, really, you're not just starting on the 4 years of college, you're starting on the rest of a lifetime of continued learning. And so that means that you have to also think about, what does that experience look like for you? It has to be enjoyable. It has to be something that you can pull from it, experiences that fill you with excitement, fill you with the energy of wanting to continue to do this and to seek those out. And so, for me personally in college, the experiences where I not only learned something in a classroom, but was able to take those experiences and build a project of my own, really helped me stay engaged and excited with the learning and apply it and actually deepen my understanding by doing these more hands-on projects on the side. Some of them were just completely voluntary. Nobody asked us to do it. It was just me and a few classmates. We just did it on the side. Others, we sought out mentors to help us go beyond what was in the traditional curriculum. And I think, going back to what the educators are asking, I think the answer is similar, which is to definitely engage the students with more than just textbook material, right? I mean, textbooks are where I like to say knowledge goes to die. And I say that as someone who writes textbooks, that by the time it's in a textbook, it's already been processed and thought over by people for a decade or two. The most exciting knowledge is the stuff that's really alive, and you only encounter that when you're doing research or hands-on projects yourself. And so, even at the undergraduate level, having a lot of hands-on experiences, project courses are important. it is important to engage students as early as possible into inquiry-driven learning, into research-based learning projects, and kind of have that be a continuous process for them. Students should learn very early on how to read research papers and appreciate the most cutting-edge aspects of technology.
Thank you so much, sir, for all your answers. I would like to take this opportunity to express my gratitude to Dr. Bhaskar for taking up time from his busy schedule and addressing all of us. It was really a pleasure to have you amongst us, sir, and learn more about IoT. We would also like to apologize to the audience for not being able to take up all the questions due to the paucity of time. Before we close this session, I request you to please share your closing remarks with us, sir.
Well, I just wanted to thank you all for having me on, and thank you Ekamjot and Siddhant for moderating the panel here, and to Mr. Ashish Gupta for introducing me, and to Plaksha University, and all the best going ahead, and to all the folks in the audience as well. Thank you so much for having me.
Thank you, Professor. This talk has been extremely engaging and insightful. I think I can speak on behalf of the audience when I say that we're a lot more aware and interested in this fascinating area that's surely going to be a massive aspect in our lives going forward. From everyone at Plaksha, I'd like to thank the audience for tuning into Tech Talks today. This is the 6th webinar in our series of conversations on how technology is empowering our changing world. Our next Tech Talk is on the 25th of July with our speaker being Dr. Sriram Rajamani, who's a distinguished scientist and the Managing Director of Microsoft Research India. Please do keep a lookout for further details. Thank you once again for tuning in. Stay safe. Good night.
Thank you.
Bye.
Bye-bye.